So today it's my pleasure to introduce Dr. Sandro Vattioni. Sandro completed his PhD at ETH Zurich in January, investigating the risks and benefits of stratospheric solar climate intervention via solid particle interactions instead of sulfur injections. His work includes measurements of uptake coefficients of nitric acid and hydrochloric acid on calcite particles under stratospheric conditions, as well as aerosol-chemistry-climate modeling to assess impacts on the Earth radiative balance and stratospheric chemistry. Sandro was supervised by Tom Peter and Gabriele Chiodo and collaborated with the group of Frank Koich at Harvard, the group of Marcus Amon at Paul Scherr Institute, as well as the group of Timothy Zakotalov at the Physical and Meteorological Observatory, Davos World Radiation Center. Currently, Sandro is on a research visit here at NCAR working with Simona Toms. Today, he will be talking about risks and benefits of climate intervention via stratospheric aerosol injection on solid particles. And before starting, I'd like to remind the people following online that you can enter your questions in the space below the video at any time during the talk. And then at the end of the presentation, I'll read those questions to Sandro. So the floor is yours.
Thank you very much for the introduction. Hello everyone. My name is Sandro. As you heard, I just completed my PhD in January from ETH Zurich, and I will present on the results from the last 4 years of work. And I collaborated with many people, which are all listed here at different institutions, which all provided funding for this research. As you know, greenhouse gases are still rising year by year, so CO2 emissions, which causes our climate to warm, and that's these dismal prospects have motivated researchers to investigate a technique called stratospheric solar climate intervention. So the idea is to inject aerosols into the lower stratosphere to reflect more sunlight back to space, and thus reduce global climate temperature, mean temperatures, and therefore reduce some risks of climate change. So this technique is subject to several environmental and also ethical risks, which first need to be assessed to better inform a policymaker about the risks and benefits of this technique. So it's a rather controversial topic. And that's what I was looking at during the last 4 years. So most research on this topic has looked at the injection of SO2, so sulfur dioxide, which then subsequently forms sulfuric acid aerosols. This is mainly due to the natural analog of volcanic eruptions, which also cool the climate. So I will first briefly report on a study that compared stratospheric aerosol injection scenarios of SO2 injections, so SAI. So this recent study of Weisenstein 2022 used like 3 different aerosol-chemistry-climate models to perform the very same injection scenario, which injected like 5 megatons of mass at between 30 degrees north and south in the tropical lower stratosphere. And you can see that the resulting aerosol burden and radiative forcing are substantially different depending on the model you look at. And this also translates in like side effects such as stratospheric warming, as you can see here. While a big part of these intermodal differences, or these substantial model interdifferences, can be explained by a different dynamical core, or different dynamics of these models, the major part is probably also due to aerosol microphysics. As you can see here on the rightmost panel, the resulting aerosol size distributions of these models averaged between in the region of injection, is very different between these 3 different aerosol chemistry climate models, which point at the importance of having the aerosol microphysics correct to assess SAI scenarios. So as you can see here, the optimal size range in green for backscattering solar radiation. The particle concentrations differ by almost 1 order of magnitude, depending on the model. So Let's quickly recapitulate the processes which govern these aerosol size distributions. After injection, SO2 is oxidized in the stratosphere to H2SO4 within about 30 days. The resulting H2SO4 gas then immediately nucleates, or it either nucleates, which would form many tiny nucleation mode particles, or it condenses on pre-existing particles, which shift aerosol size distributions to the right, to bigger sizes. And then we also have coagulation, which is important, which also creates bigger, or which shifts particle size distributions to the right. And in the end, sedimentation is the process that removes the particles from the stratosphere, and that's mainly a function of R square. So especially the large particles determine how much mass will be, what the mass, the sedimentation velocity, the sedimentation flux of the aerosol burden is. So it's now obvious that it's very challenging for these aerosol microphysics models to resolve these processes at the time scales and spatial scales which are small enough to handle these processes simultaneously. And the big differences in aerosol size distributions have motivated us to look closer at our own aerosol-chemistry-climate model, so-called AR, to sensitivity test the resulting aerosol size distributions under conditions of geoengineering, or like of injections of H2S of SO2. Like we we looked at the injection scenario of 25 megatons of sulfur per year, and what we found is when we switched the call sequence of the nucleation and the condensation routines with our standard microphysical time step of 6 minutes, we found substantially different aerosol size distributions, which you can see here. And these size distributions only converged when substantially reducing the microphysical time step. So this also translated in the resulting aerosol burden and the globally averaged radiative forcing between these scenarios, which is substantially different depending on the setup that we use for in our aerosol microphysics scheme. So it's really important to have these processes right also under conditions of large continuous H2SO4 supersaturations, because the nucleation is mainly dependent on the H2SO4 supersaturation. So having a low enough macrophysical time step is important to have this right. And this also points at potential model biases when assessing scenarios of climate intervention via stratospheric aerosol injection. Yeah, but there are also other side effects from SAI via SO2 injections. For example, stratospheric warming, which creates a dynamical feedback on atmospheric dynamics, as well as, for example, ozone depletion. However, recent studies have shown that, for example, solid particles such as alumina particles and calcite particles would result in reduced stratospheric warming when achieving for 1 watt per square meter radiative forcing. You can see here sulfur, which results in up to 1.2 Kelvin, and other species have a substantially lower absorption coefficients in the long wave radiative forcing, in long wave range. So other studies have shown that, for example, alumina particles result in substantially smaller ozone depletion compared to the injection of SO2 for a given radiative forcing. And furthermore, other studies have even showed that the injection of calcite particles could result in an ozone increase due to the depletion of HCl from the stratosphere on calcite particles. However, these studies all relied on simplified modeling and very rough assumptions, which makes them subject to large uncertainty. That's why in my PhD research I looked closer at solid particles and the heterogeneous chemistry on the solid particles to learn more about the risks and benefits of solid particles for SAI. This is the research question I want to address in today's talk. Compared to sulfur injection, what are the effects of alumina and calcite particles, stratospheric ozone concentration, stratospheric warming, and on the Earth's radiative balance? We used the following approach. So we went to the lab and performed experiments on heterogeneous chemistry at the nanoscale on solid particles. And we then used this information and implemented it in global scale Earth system models to look at impacts at the global scales. So let's first have a look at the heterogeneous chemistry on calcite particles. Calcite is a base and it reacts with the acids in the stratosphere. So HNO3 and HCl are present in the parts per billion range in the stratosphere, where H2SO4 is present at much lower concentration. HCl is the main reservoir species of chlorine species, of chlorine in the stratosphere, and it is also the end product of chlorofluorocarbons, which are responsible for the ozone hole that is occurring every year. So removal of chlorine from the stratosphere via uptake on calcite particles and formation of these salts could have the win-win situation of like healing or accelerating the healing of the ozone hole while simultaneously cooling the climate. However, there is also HNO3 in the stratosphere, and the uptake of HNO3 with subsequent formation of calcium nitrate would remove NOx from the stratosphere, and reduction of NOx would decrease the N2O2 concentration, which under present day ODS concentrations would decrease the deactivation of active chlorine, and therefore we get we get more ozone depletion when we take up HNO3 on calcite particle, or when we remove HNO3 from the stratosphere. So it's really important to quantify the uptake of these acids under stratospheric conditions on calcite particles. And there were previous studies which have looked at that and found uptake coefficient of 10 to the minus 1 to 10 to the minus 12 for these acids. However, only few of them have looked at the uptake coefficients under stratospheric conditions. An uptake coefficient of 10 to the minus 1 would remove the whole reservoir species in the stratosphere of these acids within from the stratosphere within days, while an uptake coefficient of 10 to the minus 6 and lower would not do much to stratospheric composition. So it's really important to quantify these uptake coefficients under stratospheric conditions, like temperature and also relative humidity, and also as a function of time, because there might be a passivation effect with time. As you can see here, if you take up these acids at the surface, and you could form these salts at the surface, which would passivate the interior of the particle from further reaction. So you could seal off the interior of the particle, which would decrease the uptake coefficient over time. So for this, we need surface-sensitive measurements techniques to quantify this, which allow to measure the composition of the sample as a function of depth, to also quantify the diffusion processes into the sample. So we want to measure the uptake coefficient at stratospheric concentrations temperatures and relative humidities of these acids. And the goal is to measure the uptake coefficient as a function of time. For this, we have used ambient pressure XPS, ambient pressure X-ray photoelectron spectroscopy, and heavy ion elastic recoil detection analysis. So while APXPS has a lower depth sensitivity, it can measure the composition of the particles in situ during exposure of the particle surface to these conditions. On the other hand, heavy ion ERDA has a larger depth sensitivity of about 200 to 300 nanometers, and it can only measure the samples ex situ after exposure to these conditions. So in the following slides, I will report on the uptake of HNO3 on calcite surfaces with these two measurement techniques. So this is our reference sample, calcium carbonate sample, and you can see here the elemental composition measured with ERDA. And it's like the typical elemental composition of calcium carbonate with 60% oxygen, 20% calcium, and 20% carbon. And if we now look at the sample which was previously exposed to 0.8 ppm HNO3 for 10 days, that's about 100 times stratospheric concentrations, you can see a clear diffusion profile, or a profile of the nitrogen concentration as a function of depth. So the profile looks like a diffusion profile, and you can correlate this this curve with a diffusion coefficient, and the resulting diffusion coefficient is about 10 to the minus 17 for this setup, or for this setup, which points at the importance of diffusion processes when investigating the uptake of these acids. So then, in our next sample, we looked at 8 ppm HNO3, like 10, which is about 10,000 times stratospheric concentrations. So 8 ppm for 10 days, and you can see that the whole calcium nitrate, the whole calcium carbonate was gone. So there is no carbon anymore in the whole depth profile here, down to depths of 240 nanometers. But we can see a lot of nitrogen and also hydrogen, which points at the importance of hydrates, which contribute in the reaction pathways. And we then measured the sample again after storing it for 10 days in vacuum, and even though it was in vacuum, we could nothing should have happened to this sample. We measured a very different concentration in the sample in the sample composition. We can see that carbon continued or started migrating towards the surface again, since the concentration of carbon is dropping to the surface. So it came from the interior of the sample to the surface, and nitrogen continued to diffuse into the sample. So yeah, this shows that on these like time scales of 10 days with the very large H2S and HNO3 concentrations, that diffusion processes play an important role, and also the hydrates play an important role. So now we move to the ambient pressure XPS measurements. The ambient pressure XPS setup at the Swiss Life Source at Paul Scherrer Institute allowed for the first time to measure the uptake of HNO3 under stratospheric conditions in situ as a function of time of up to like 1 day. And we have measured different samples, which were like exposed to different concentrations of HNO3 So from 0.6 times stratospheric equivalent concentrations to about 17.6 times stratospheric equivalent concentrations. And as you can see, the resulting calcium nitrate layer is between like 0.2 and 2 nanometers after 1 day, which is very small. So this would only translate to an uptake coefficient of about 10 to the minus 4 to 10 to the minus 5. However, what we also can observe is that the signal flattens out with time, which points at the passivation effect with time. So we have a decrease in uptake with time, which indicates the passivation effect. So what we now did is we put our measured uptake coefficients, so from Aerodyne XPS here in green, into a table together with all previously measured uptake coefficient of HNO3 and HCl on calcite, and put it into this figure as a function of the exposure. The exposure is the concentration times the duration applied in each experiment. And the black line shows the correlation with all this. So there's a linear regression on the log normal on the log scale of this axis with all the measurement points. And there is a clear picture which evolves that particles which are freshly exposed to the stratosphere or to conditions to HCl and HNO3 start with a very low uptake, with a very high uptake, and the uptake then continuously drops as a function of exposure, and due to increased importance of diffusion and passivation with time. So if we now look at the equivalent exposure of a calcite particle in the stratosphere, assuming a 1 year lifetime or stratospheric residence time of the particles, we would end up at exposures of 10 to the 17 for HCl and HNO3. And if we look what the resulting uptake coefficient would be at this exposure, we end up with about 10 to the minus 4, an uptake coefficient of 10 to the minus 4 for HNO3, and about 10 to the minus 5 for HCl, which is rather low. So what does this mean now for the global stratospheric ozone concentrations in the stratosphere? And for this, we have, to look at this, we have developed an aerosol, a solid particle microphysics scheme, and implemented it into our aerosol-chemistry-climate model, so-called AER. So the model interactively simulates all chemistry relevant to reproduce stratospheric ozone, and it also contains a sectional aerosol module. We have implemented solid particles. They can agglomerate in the model via coagulation. They're subject to sedimentation, and in the troposphere they're removed via dry and wet deposition. They also interact with radiation in the long wave and short wave range, and we also account for heterogeneous chemistry taking place at the particle surface. This allows for the first time to interactively simulate feedbacks between all these processes online in one model. And with this, we can also assess like climate impacts or ozone feedbacks on climate at the later point of solid particle injection scenarios. So what we did now is we used that model and assigned, we injected 5 megatons of calcite particles with a radius of 240 nanometers. And we used year 2020 ozone depleting substance concentrations and greenhouse gas concentrations. And we assigned these uptake coefficients, which we found most likely on calcite particles for these acids. And we simulated a scenario, and as you can see, the total ozone column as a function of latitude does not significantly change due to from this scenario. However, these uptake coefficients are subject to substantial uncertainty. So if diffusion would be very efficient, we could get uptake coefficients of about 10 to the minus 3 for HCl. And if we would apply this uptake coefficient, you can clearly see an increase of about 25% in the total ozone column in the southern hemisphere in a global annual mean, and which would be a significant healing of the stratospheric ozone hole. But on the other hand, on the lower end, the lower limit of the uncertainty range, if we apply an uptake coefficient of 10 to the minus 3 for HNO3, we get ozone depletion due to less deactivation of chlorine. So ozone depletion of up to 10% over the poles. However, the most likely scenario will lie somewhere in between, around the zero impact line. So this, yeah, and we also performed SO2 injection scenario for comparison, 5 megatons of SO2 per year, and that results in larger ozone depletion of up to 7% over the poles. So let's also quickly have a look at the heterogeneous chemistry on alumina particles. Because other than calcite particles, alumina particles, alumina is not a base, so it does not react with the acids in the stratosphere. So the bulk properties of the particles will remain the same over the course of the stratospheric residency. So, but nevertheless, the particle can interact with, for example, sulfuric acid. So sulfuric acid could condense on the particle surface, which would cover the surface with sulfuric acid. So from our sensitivity analysis with injection of 240 nanometer particles, so 5 megatons per year, we get about a 10 nanometer thick coating on sulfuric acid on alumina particles in average in the lower stratosphere. However, we also did measurements on the contact angle of sulfuric acid on solid particles, and what we found is that the contact angle is rather steep, with 30 degrees, and therefore sulfuric acid rather contracts and forms like islands on these alumina particles, and is not equally distributed over the whole particle, which leaves room which leaves surface for heterogeneous reactions on alumina surface. So, for example, chlorine nitrates plus HCl, which activates chlorine, which could result in substantial ozone depletion. And to assess the effect of this reaction on alumina particles, we made use of a previous study, Molina et al. 1997, which looked at this reaction on alumina particles, but from space shuttle exhaust. So space shuttles can also inject alumina particles, and they quantified the effect on space shuttle emissions on the ozone, on stratospheric ozone, and therefore measured this reaction on alumina particles. And they found these are the measurements, the measurement points they made, so the uptake coefficient of chlorine nitrate. And these are their measurements, so about 0.02 is the uptake coefficient, the average uptake coefficient. But they measured at HCl concentrations about 1 order of magnitude larger than in the stratosphere. So that would be the stratospheric range of present HCl concentrations. They measured at larger HCl concentrations because space shuttle also emit chlorine, so they applied slightly larger HCl concentrations. So, and previous modeling studies have just used, or previous studies which looked at the SAI via alumina particles have just used this uptake coefficient of 0.02 and applied it on the alumina particles, but this is not valid, because you somehow need to extrapolate these values to uptake coefficient to the stratospheric partial pressure range of HCl. And this could be done, or this can be done with, for example, a Langmuir-Hinshelmuth description of adsorption and reaction, which you can see here. And we did that, but most of these parameters here are unknown. So what we did is we just parametricized we took all these parameters in a fitting coefficient beta, and fitted this equation, this Langmuir-Hinshelmuth parameterization, to the data, and that's what we got. So a rather high uptake coefficient in the stratosphere, but this only accounting for the HCl concentration like this would infer, or would mean that we would just assume that the HCl would be adsorbed at the surface, and then it would react with a colliding chlorine nitrate molecule and then release the chlorine and HNO3. But this might not be correct, because the chlorine nitrate likely dissociates, and the HCl likely dissociates at the particle surface. And if that would be the case, we would get a square root dependence on the partial pressure of HCl, which would reduce the uptake coefficient in the stratospheric range of partial pressures. And furthermore, HCl is not the only acid present in the stratosphere in this system. We would also have HNO3 at even larger partial pressures, which would displace some of the chlorine ions at the surface. And therefore, the uptake coefficient of this reaction under stratospheric conditions would further decrease to probably very small values if we would also account for the co-adsorption or co-dissociation of HNO3 at the surface. So, similar to calcite particles, we perform the sensitivity analysis, what this means for the ozone concentrations in the stratosphere. And if we would assume the very high uptake coefficient, we would get ozone depletion of up to 16% over the poles. But most likely, we were rather in the lower range, so also around the zero impact line. But these results are subject to high uncertainty, and that's why we need better and more accurate measurements of these reactions on solid particles under stratospheric conditions. So in this slide, I show the combined uncertainty ranges of alumina and calcite on stratospheric ozone concentrations. And we did a similar sensitivity analysis for SO2 injections by assuming realistic uncertainty ranges for heterogeneous reactions on sulfuric acid aerosols in the stratosphere. And this is the resulting uncertainty range which we get for the sulfuric acid, or for SAI via SO2 injections. And you can see that the uncertainty range is much smaller. So even though the impact on stratospheric ozone is likely larger from SO2 injections, the uncertainty range presently is much lower, much smaller, which one might conclude that currently the use of SO2 would be much more safe. So we also looked at the same scenarios under future ODS and greenhouse gas concentrations, under 2090 concentrations of a SSP 8.5 scenario, and you can see that the impact significantly decreases due to decrease in ODS concentrations in the future. And most remarkably is that the difference of the two reference scenarios of 2020 and 2090 is larger than any of the perturbation experiments which we performed. But this is also a very extreme scenario of climate change. So just to show this as well. So to quickly come back on the research questions which I posed in the beginning. The impact on the radiative balance and stratospheric warming and stratospheric ozone from solid particles compared to SO2 injections. So when we have 1 watt per square meter of cooling we require larger injection rates of solid particles, of alumina and calcite particles, because they have a larger radius and a larger density, and therefore sediment or settle much faster. So we only need smaller burdens of the solid particles compared to sulfuric acid aerosols, but larger injection rates because of the significantly reduced stratospheric residence time of the solid particles. However, the big advantage of the solid particles is the significantly reduced stratospheric warming, as you can see, which is especially true for calcite particles, which only 0.7 Kelvin compared to 2.6 Kelvin in the case of SO2 injections. Here in the upper part of the figure, I show the total ozone column of the our reference scenario in a global mean, 370 Dapson units, and the historical minimum in the beginning of the 90s due to the combined effect of the Mount Pinatubo eruption and the emission of ozone-depleting substances. And here is the uncertainty range, which I showed on the previous figure already, but normalized to 1 watt per square meter radiative forcing. And yeah, the most likely scenario would be a rather small impact, but the uncertainty range is much larger for the solid particles. So I said the main advantage of the solid particles, of the solid particle injection, is the reduced stratospheric warming. This is mainly because of their reduced impact on stratospheric dynamics. So let's, in the end, quickly have a look at the dynamical impacts of solid particles. For this, we look at the optical properties of different particle candidates, like, for example, diamond particles in gray, or alumina and calcite here. And there is so what I show here is the normalized backscattering cross section, so normalized to the particle mass and the stratospheric residence times, and weighted with the incoming radiation in each wave band of our chemistry climate model. So these are the short wave bands of our chemistry climate models. So, for example, diamond would be a good candidate. Here in gray, it also has a very low absorption in the short wave length, while, for example, titania or silicium carbide have a very strong absorption of solar radiation, which results in warming, stratospheric warming. And also in the long wave range, so these are the long wave bands of our model and the atmospheric window, you can see that diamond particles results in very little absorption. And while other, for example, sulfuric acid here in the top results in significant absorption and thus warming. So diamond particles seem to be a suitable particle type with good optical properties. So what we did is we performed a G4-like geomip simulation. So that this means that we injected mass to get into the stratosphere of these particles to get 1 Kelvin of cooling at the surface. So 1 Kelvin of average global surface cooling within SSP 8.5 scenario. And we looked at the difference of sulfur versus diamond impact. So this is the temperature anomaly you would get when injecting sulfur to get 1 Kelvin of surface cooling. So you can see here in the troposphere we have cooling of about 1 degree, as well as in the calcite in the diamond injection scenario. and the stratospheric warming is significantly reduced in the case of diamond. This also translates to the zonal wind perturbation. We get significant increase in the jets here in the upper stratosphere from SO2 injections, while in the case of diamond we see more a reversed climate change effect. Also the age of air, while the warming here causes the age of air to decrease, so a faster Burrow-Dobson circulation, we have like here the impact of the tropospheric cooling, which increases the age of air in the stratosphere. And the warming in the stratosphere also translates to the water perturbation, water mixing ratio perturbation in the stratosphere, which is significantly larger in the case of SO2 injections compared to diamond injections. And when looking at, for example, pressure differences at the surface, you can see that the impacts on surface pressure are also reduced, especially in high latitudes. A significant feature, or a prominent feature, is the northern annular mode here, which was shown previously to be a result of stratospheric warming, so the big positive anomaly, pressure anomaly here, which is significantly reduced in the case of diamond injections. And we also see significantly reduced perturbation of the precipitation minus evaporation in northern or in high latitudes, while in the tropics the pattern is quite similar to SO2, and this might be mainly due to the injection scenario, the equatorial injection scenario which we applied, and this could be improved with by injecting at different latitudes, for example. Yeah, so it looks like several of the negative impacts from stratospheric warming could be reduced by, for example, injecting diamond particles or other particle types which do not warm the stratosphere as much as sulfuric acid aerosols. And let me quickly give a quick outlook at the end. So the big uncertainty or the big limitation of our study, of our modeling study, is that we just inject our aerosol particles or solid particles as monomers into the grid scale of our chemistry climate model, which has like a horizontal resolution of 200 times 200 kilometers. So we do not account for sub-plume scale processes, such as like dispersion of the particles into the stratosphere, for example, from aircrafts. These small particles could have large van der Waals forces, which make them stick together. So we need to find ways how to really disperse them without making them clump together and falling, so that they fall from the sky like stones. That wouldn't help. So we need coagulation experiments and large eddy simulations which resolve these processes to look at these processes in detail to really assess the efficiency of SAI via solid particles. This is very important because the higher order agglomerates you get, the more decreases the radiative forcing efficiency. So here you have monomers of a certain size, and their agglomerates, like the more agglomerates or the larger your agglomerate grows of particle, the more forward scattering over backward scattering you get, and therefore the efficiency, the backscattering efficiency of these particles decreases. So you want to avoid agglomerations, which could be challenging within an aircraft plume. But I mean, there is still a lot of research to do, starting from the plume, the sub-plume processes to the grid scale of the climate models. So we need to have better measurements of optical properties of the resulting aerosol solid particles size distributions, as well as, for example, as well as ice nucleation properties of these particles are also important, because these particles, upon sediment or settling back into the troposphere, they could interact with, for example, cirrus clouds, and they could like thicken or thin the cirrus cloud, which would create positive or negative feedback on radiative forcing, which is highly uncertain. And also, as I have shown, heterogeneous reaction rates are still very unknown, and we need to have better measurements of these quantities under present and future conditions of stratospheric conditions. And this needs to be done to better inform our Earth system models to really look at the impacts of SAI of solid particles at the global scale. And with this, I want to close and thank you for your attention. I'm happy to answer some questions. Thank you.
Are there any questions from the audience?
Really nice talk and a lot of information. So how important is it, in a lot of these models they use model schemes for the aerosols. How important would it be to everybody to switch to, you know, a bin model approach like Karma?
Yeah, I think that's very important to really resolve the aerosol size distributions. I think that's also what Simone recently updated CESM by so coupled Karma interactively to CESM, and that had a big impact on the resulting aerosol size distribution under SAI conditions, and which shows that having the aerosol microphysics resolved good enough is really key, especially for research on stratospheric aerosol injection. Yeah.
So the stuff you showed today was mostly modal aerosol modeling?
No, that's all sectional aerosol model. Yeah,
okay, great.
Except for the first, the three models which I showed in the first two slides, the model intercomparison study, their CSM and ECAM, they used modal models, and our model is a sectional one. Yeah.
Excellent. Thank you.
Yeah.
Yeah, that was a lot of information. Thank you. So you did surface studies with alumina particles and calcite particles, and then later in the talk you switched to look at the radiative impacts of diamond particles.
Yeah. Mm-hmm.
Do you expect any surface effects with diamond particles?
I think they might be similar to the ones of alumina particles, because I don't expect diamond to undergo like reaction with acids in the stratosphere, but this needs to be tested. I don't know. But I expect them to behave similarly as the alumina particles, so that they like host sulfuric acid at the particle surface, but also they might have like room for, or there might be surface for direct heterogeneous reactions on diamond particles. If you can, yeah, if this can be distinguished at all in reality, yeah. So I only switched to the diamond particles for the last part because they have better optical properties and show the real potential of solid particles. There might be other materials which we don't know yet that have even better optical properties or similar as calcite, as diamond, and this also needs to be investigated. Mm-hmm.
We've got a question online. Might it be possible to cool certain regional latitudes that are deemed too hot and allow others deemed too cold to continue to warm? For minimal energy consumption, is there a defined optimal global temperature?
So, yeah, No, there's for sure not a defined optimal global global temperature, and that's what I maybe also try to make clear in the beginning of the talk, that this technique, so stratospheric aerosol injection, is subject to also ethical considerations. So who decides on what is the optimal temperature? But I mean, there are many studies which show that that a variety of like impacts from climate change could be reduced from stratospheric aerosol injection. So if we would do some stratospheric aerosol injection, but these results are subject to uncertainty. And there are also other studies which show that that SAI could do more harm than benefit. So it's we definitely need more research on this, and but there is no global no optimum global mean temperature. But I think our society would be better off with a temperature, with global mean temperature that we have today, or like that we had 30 years ago, compared to the one like 2 or 3 degrees hotter that we might expect in 100 years from now. Yeah.
So there's another question online. Would the aerosol and SO2 be able to be injected at the same altitude, or would there have to be a difference for gas versus particle phase?
So we assumed the same injection altitude, about 20 kilometers. So we would need to have specialized aircrafts to carry these payloads to these altitudes. And but we didn't look at like sensitivity to the injection altitude in our study here. Yeah.
So I noticed when you showed the global maps near the end and the difference between SO2 and one of the solid particles, that both, that one, yes, on the right, both, if I understand it right, both scenarios show a decrease in moisture in the Amazon. That suggests that it would be harder to keep the CO2 under control.
Yeah, so you mean this decrease here, yeah?
Yeah.
Yeah, exactly. So I think previous studies have shown that so we applied, we injected our injections in the equator here between 10 degrees north and south in the tropical stratosphere. And therefore, we probably also get the most perturbation in this area. And previous studies, other studies have shown that if you inject at higher latitude, you could like get rid of such effects. Not completely, but you could reduce them. But these are very preliminary results. So I have not looked into the details of them, like of their impacts.
Yeah, maybe one comment to add there. It's also, I mean, the main difference, it's one model, and one heats more and the other heats less in the stratosphere. And we know that there will be differences when you have less heating, you get less, usually, precipitation effects. But if you look at the other model, like if we eventually run it maybe in our model with the same conditions, we may get opposite results, even though we do exactly the same injection. Yeah. And that still has to be understood on what is really actually causing regional changes and precipitation changes. So that's a whole other research question that has to be addressed. If I mean, you can comment.
Yes, exactly. So this is only a 30 years average of one model. So if we would have other models to compare, you might get different results in these models. So.
So a question online regarding effects on vegetation and crop yields. Am I right to conclude that effects should be less with calcite and diamond particles because they absorb less solar radiation than alumina and SO2?
So the absorption of solar radiation would result in stratospheric heating, and I think the crop yields are mostly sensitive to, like, I'm not sure, I'm not an agriculture specialist, but I would suspect like temperature changes at the surface and maybe diffuse radiation changes, as well as maybe ozone, so UV increased changes. And what we found, so the temperature anomaly is what you aim for. So you want to have lower temperatures. And what we found is that you get significantly reduced diffuse radiation alteration with solid particles compared to SO2 injections, if it's possible to have the particles in a monodisperse, so as monomers in the stratosphere. Because once you form agglomerates, they have a lot of diffuse like forward scattering, which creates diffuse radiation. That might then be another problem. But from our results, we found that solid particle injection results in reduced diffuse radiation compared to SO2 injections, and also most likely reduced ozone depletion, which would restore like the UV radiation at the surface.
Are there any other questions from the room or online?
Hi, this has been a terrific seminar. Thank you. So I have kind of twin questions. I'm curious to know if you can simulate what would happen if this suddenly stops. So let's say your SAI loses funding for some reason or support or whatever. And the other side of that is what happens if you get something unexpected, adding particles like a volcanic eruption, pyro-CV, or limited nuclear war. Can you account for either kind of scenario when you're doing this kind of simulation?
I mean, we could definitely simulate this, and there have been previous studies which looked at this, especially the sudden termination effect. So if you would stop out of whatever reason from one to the other day, that would create, obviously then you would have the climate change that you compensated over this period of time. You would then see like only within 2 years, and that would be a very catastrophic scenarios. But I don't know how likely or unlikely such a scenario is, but it's definitely, one would definitely need to consider that if you want to start doing that. And the other scenario, in my opinion, I think when we have like nuclear war or like such a major volcanic eruption that then we will likely have other problems than like SAI, and that in that respect, I think we might be on the safer side. But definitely we need to look at the combined effect of SAI and volcanic eruptions and what this would do, because volcanic eruptions happen every now and then. Yeah. Yes. Yeah. Yeah.
I'd be interested to know if you guys have thought about which technique would you use on a plane to spray the particles, and if that needs to involve some sort of medium in which the particles are suspended or not.
Yeah, so that's what we are starting to look at now. So how, if it's possible to disperse these particles in like as monomers or like in size distribution with as little as with very little agglomerate formation. And most likely you would need to, or one of the scenarios to deploy this from an aircraft is with a carrier gas, that you have these particles in a gas already suspended. or a carrier liquid that evaporates, but then you automatically create like a perturbation to the stratosphere, which might be not what you want. So we are currently looking into that, but I think no one has really done that before, because that would be the thing to, the most crucial thing to look at whether it's possible at all. Other scenarios would maybe, which might be possible, or so I'm not an engineer, but if you have like balloons with vessels and you pump the solid particles suspended in air to the stratosphere, but I don't know about whether this would be possible and what the side effects of this would be.
Are there any other questions from the room? Well, if not, let's thank Sandro again for a great talk.
Thank you.